start hitting record then. Hi, everybody. Sorry for the delay, but I think we're going to make it work. That's the theme, right? No matter what happens, we're just going to make it work. So welcome to your first formative assessment review session. Everyone did it on time-ish. I'll give it to you. If it's before I see you, it counts as on time enough. That's the goal here. 3 points for making an honest effort, which all of you did, so thank you for that. Bladimir is going to lead us through a discussion. This is your chance. If you want clarification on things or if you want to ask further questions, please feel welcome to do that, even if it wasn't a specific prompt. So I will let him take over, and I don't have to monitor a Zoom room because there isn't one. So
I got one. Yeah, that's weird because now we say, hey, roomers, not Zoomers.
Exactly. Here, I'm gonna, go ahead.
Thank you, Lisa. Hi, everyone. I hope you're having a great day. Today, we will check some of the potential or, well, not good or correct answers, but some of the answers that we were expecting for formative assessment 1. Here I have a list of all the 5 questions, some ideas that we can share, and sorry for the presentation, I have something better. So for instance, here the answers, you can read them, but that wasn't intended. Although we read your answers, they were okay, so thank you for your time, for your effort. If you have any question and you are while you are working on your formative assessment, you can ask questions, okay? We can talk about the different things you are thinking and the different ideas you are considering. So thank you for your time doing this. Let's start with question 1. If patients from a single hospital clinic are randomly assigned to one of 2 groups, how many levels of a model would you need to predict patient outcomes? 1, right?
Bigger question, right?
Yes.
Only because you did not read the part in parentheses. It's extremely important to say 1.
Yes, that would be my question.
Yeah.
To see if there was
If in the
2.
same clinic there were more than 1 physician, then would be 2 levels, right?
Ah, yes, there you are right. It could be if we have more than 1 physician for the same hospital. Although in terms of sample size, I don't know if that would be possible. Because for instance, when we have a classroom here and you have, let's say, 2 instructors, Lisa and I, we could have 2 levels because different people could be assigned, classes with different teachers or trainers, even in the same classroom. Although with 2 units at level 2, in this case instructors, or let's say 3 or 5 physicians, I don't know if that would be feasible in terms of multi-level modeling. Do you know what I mean? Questions?
It may not have a lot of power, basically. Is that what
Exactly,
you're
yes.
saying? Because you have too little for what you're trying to measure, or if you're trying to measure anything.
Yep, it depends on sample size too. But yeah, you are right. Maybe we have a large hospital, we could have a lot of physicians and we could have a lot of patients. So in this case, for question 1 is 1 level. It is a single level model, which is also known as a one source ANOVA for those in design of experiments, or just a simple linear regression. Good.
Can I add something?
Yeah.
So if we had like 2 providers of control and 2 providers of treatment, right? Technically that starts to look like a level, but 4 is not enough. So that would be a case where just putting in a fixed effect as to who you saw would be a better way to address it, and that would keep it as a single level model.
Yeah, multi-level modeling, yes, Usman. Now, multi-level modeling is just one option to analyze hierarchical or cluster data. You also have the fixed effects approach, and you could use cluster robust standard errors, and you could use hybrid approaches. For instance, when you have 3 levels, 3 level data, for instance, students in classrooms in schools, you have enough students, enough classrooms, but not enough schools. It doesn't mean that schools won't matter. They will. The thing is, let's say that we have 2 or 3 schools. What we can do at level 3, we can use a fixed effect approach to use the school IDs as fixed effects at level 2, and we can have a multi-level model between level 1 and 2. Students within classrooms, and level 3 would be included as fixed effects at level 2. That's known as the hybrid approach in a Magnish paper in your reading list. Common something. Sorry, but it's Magnish 2023. Usman.
Yeah, so I'm trying to think about this situation where you have a community college, so if you collect all the data if we divide the data into two teachers of that college, then I'm assuming it's going to be level 2. Because teacher 1 and then teacher 2.
It depends.
Okay.
Because what's the nested structure there? You are saying we have one institution and we have students nested in teachers.
And 2 teachers within that institution. And you try to collect data from those 2 teachers within one institution. So how do you see the levels there?
Yeah, that could be, but just 2 units. That's not enough to me. If when you have just 2 teachers.
Like that's the same as the story, treatment or control, teacher 1 or teacher 2.
So how about if we spread the branches of that college? Let's say if that college has 5 or 6 different branches.
That would be like question 2, right?
I think so. We're heading it that way. It depends on how many is the answer.
Yes.
Now, if those instructors had different sections in which they taught one section one way and another section a different way, now you're looking at multi-level, I think, yes? Because of that structure? Potential. Okay, fair enough.
Yep, and I think that yeah, Mubarak.
From his question, saying that we have a community college and collect some data without having structured or cluster sampling. But let's say after you collected the data, let's say you have 500 organizations from the school, who is announcing information from this community. And then you get the data back and you're seeing that, oh, out from this data set, I have, let's say, departments. Can you then go ahead and say, okay, now, although I was not making the multi-level at the beginning, can I now make the decision to go multi-level after I have seen the data? So, oh, there are some things, and now I want to go multi-level.
What do you say, Larry?
I think so. If that's relevant, but that's another thing. Now that you're mentioning that, I'm thinking about the background in the research that we do, because here we are thinking almost from a design perspective. We are almost assuming that we are able to make decisions when we are collecting data, although most of the time what we have is just data. So in my case, for instance, in research, we have discovered sometimes that regions in the data we have are relevant. Regions are collection of cities, in Chile at least. When we find that, what we have done is we must make a decision about how to control for that clustering. So for us, if that's relevant, I think that we should do something. Now, most of the time, I've also seen people that uses traditional regression models to analyze cluster data, even when they have students in schools, for instance. So I think that we should do something, but at the same time, that depends on if we are aware of what the clustering or what the hierarchical structure in our data is. And that depends on the knowledge we have about that data too. That's what I would say.
Yeah, I would agree with that. I think that just because you didn't anticipate a design effect of some kind doesn't absolve you from caring about it and doing something about it.
Yeah.
But you would have to have some kind of a priori knowledge based on the sampling plan and based on how data collection went to understand what the possibilities are as to how people could be clustered together. So that part still is kind of top down.
Yes, that's interesting. And I remember that last 2 years ago, we were working with some data from Chile, and we found out that there were significant differences between regions because we were working with a national weight data, and that's something that in the literature wasn't mentioned, that regions could be something, and it was, so we use a demeaning approach. We use like cluster mean centering variables at level 2 to avoid the level 3.
Stay tuned for Thursday on that.
Yes, centering approaches. Yes, question.
Question.
Yeah.
First one is, would you mind say that again? Why, if there's like 2 different positions, it's not necessary changing that to create that to a multi-level model. And the second one is, would it individual differences creating a level, like a multi-level?
Regarding the first question, I wouldn't say that a 2-level is not needed. Because in this case, it's by the same physician. But let's say that you have 2, you could use a fixed effects approach, or you could add the teacher's ID as a fixed effect variable. sorry, the physician, like in the in the treatment case. That's what I mean. What we were talking before was how much is enough. I think that's the question when you have a hierarchical structure. Let's say that you have students in a classroom. Maybe students in 2 classrooms is not enough to fit a multi-level model, but it
Sample size.
exactly. But it doesn't mean that those 2 classrooms are the same thing. They are not. But the thing is, can you fit a multi-level model with a sample size of 2 at level 2? I've not seen that. And
But it's not because the differences between two positions.
yes,
They're creating like a different level because the data is clustered, but it's not necessarily fitting to the model because it's sample size.
I think so.
Yeah, I think it's a distinction of how the data are collected versus what you end up doing per model. So it is true that in this first question, let's just say it's one hospital, one provider, just go simple. People are nested in either the control group or the treatment group, right? So from the face of it, yeah, there's a group level sampling, not really because there's only 2, but let's say group level and then there's people level. But once you put in a dummy code as a predictor and give it a fixed slope as to whether you were in treatment or control, there's no more remaining group differences. You saturated them, you've eliminated them completely, they're gone. So then all you have left is individual differences among the patients, which is level 1, which is like what we always talk about in regression or ANOVA. We don't use levels, but like just that's what the model is for, is patient differences as the. So, and then the contrast to that would be the question 2 sort of design, in which case we have a different situation.
Yes. So
Does that help?
Yeah, so the individual differences is there.
They're always there.
counting there as a level.
Yeah, individual difference is level 1. They're always there as long as you have more than one person.
Okay.
And then the question is what's below it if you have repeated measures,
Okay.
or what's above it if people are in clusters.
Okay.
yep. Thank you. So question 2 says, what if the previous study were extended to 50 hospitals in which 25 hospitals were treatment sites and 25 hospitals were control sites? Then how many levels of a model would be needed to predict patient outcomes? Right now we have 2 levels. But why? Why now we could have 2 levels?
Hospitals have different protocols. I mean, that's true. I mean, if you talk to any nurse, say, okay, yeah, I moved from here to there. How do you do it here? Even though if they wash hands there this way, they wash hands differently over there. And so how they do things is going to make an impact, or potentially make an impact.
Empirical question, very least.
Yes, yes, it is an empirical question because now we could have within hospitals or within treatments, no, would be within hospitals variation and between hospitals variation. So that's an empirical question, but now we could have something like that given that we have a larger sample size. Although to me this was tricky because when I read this thing, I thought that, okay, now we have 50 hospitals, but 25 of them, half of them are control and 25 are treatment. I thought that the treatment and hospitals could be confounded in this case because it is the same thing, although
Random assignment to hospitals is the idea.
yes, but here treatment would be a level 2 predictor because now it's a hospital attribute. So people within hospitals would be assigned to one treatment, and treatment would divide hospitals into groups. So to me, this is like in the case of schools, when you have school dependency, you can have private or public. It's the same thing to me.
But then I'm thinking after you have removed the effort, it has been the treatment of control group. I believe there is an outcome that is interested. And that outcome will vary within and between hospital, even within the treatment group, and will vary within and between hospital in the control group as well. So that was what I saw. Now it makes sense why the two.
Yeah, I think that's a really good point. Can you please repeat that for the recording?
Yes, of course. In this case, we know that treatments are a level 2 thing, a hospital thing, but the outcome can be something individual in which we can have within hospitals variation and between hospital variations, and the treatment can be affecting that outcome.
So what if a hospital has multiple doctors performing this? Now are we at level 3 with some things?
Hospital would be 3, doctors would
But
be
yeah,
2.
but, yeah, but
Assuming
I'm
they
just
only
saying
work at one place.
Yes,
and
exactly.
also, I know doctors who work in Cedar Rapids, they work at both Mercy and St. Luke's. And so,
Yeah, that's the advanced class, that's not.
that's not us, but that is a thing that is taken care of at some juncture.
Yeah.
Okay, fair enough.
The same technology can be leveraged to stack the Lego blocks onto this design however we need it.
Yes.
Yeah.
Usman.
One question that I'm just thinking about, is it important to have treatment and control groups for 2 level? Or can we also have some other categories that can define 2 levels?
Yeah, you can have more than one attribute for sure.
Okay, attributes can also define levels.
Ah, no. I would say no because attributes like variables are unit characteristics. So let's say they are sampling dimension attributes. By sampling dimension, I mean level. So let's say that hospital can have a population maybe that they attend.
Oh, can I use my Grey's Anatomy's knowledge?
Yes,
to
you
answer this
can.
question, please? Because I've watched all of Grey's Anatomy twice. Okay, that's commitment. We're starting like season 20 million or something. But anywho, so like why this would still be a multi-level model is that maybe if I got treated at Seattle Press, my outcomes are different than if I got treated at Gray Sloan. Even though I'm being treated and it's supposed to be the same, people who got treated at the same place are probably more alike in how their outcomes function than people who got treated at different places. So there's variation left over across hospitals beyond just treatment versus control. So that's what makes it a model. And I think that's what you were trying to say as well, right?
Do you mean random effects?
Yeah, so that like what makes a level is variation across those sampling units left over after you've put in the model predictors. And so I think you're calling attributes predictors. I think you can put those onto the same language. You can have, if you had 50 hospitals, you could have 49 measured attributes about hospitals that could become predictors. And you would have however many people minus number of hospitals minus 1 people predictors that could go into the model as well. And so several of you mentioned that in your answers that treatment is a level 2 predictor, and that's exactly right. That's where we're headed next in lecture 2.
Yes. Now, given this context, I could ask what's level 1?
What's level 1? Patients.
Yeah, but we are assuming if they were randomly assigned, we are assuming that individual attributes shouldn't play a role in the outcome. But we could analyze that, right?
Yeah, so there's nothing that stops you from putting in whatever patient level covariates would matter for predicting this outcome because you're randomly assigning at the level of the hospital. So yeah, you're not doing anything to try and control people.
Yes, great.
Because the reason you would pick such a design is that you would not have confidence that a treatment provider could do a control version for one patient and a treatment version for another and not have that get screwed up. So it can be cleaner from an experimental point of view to assign at the top level, but then you're losing control the further down you get because you can't control who's in that hospital unless you randomly assign people to hospitals, and at least in this country that's not happening.
That makes sense, yeah.
So.
Great answer. Thank you, Lisa. Question?
If we add one more letter on PCP, like Joseph said, if then the slope of the patient and the hospital will be different in level 2 model and level 3 model,
That could be an option, yes.
then could you give us some examples and how should I interpret the results in the level 2 model and level 3 model?
Yeah. Now, that's interesting because level 2 right now is the higher thing in our model, hospitals. So let's say that we have at level 3 counties maybe. That can be something. So,
As you said, like if level 3 is a treatment,
yeah.
just you said the level 3 could be a treatment and control, right?
Oh, sorry. That's not correct, I think.
That is not correct.
Yeah, maybe if we have a lot of treatments and you allocate different hospitals, but that would be too complicated. But I think that if we would like to work with a 3-level model, we could use counties as the 3rd level because we can have hospitals. Well, I don't know if that's possible.
So I think he's actually
States in
giving
hospitals.
the hybrid example back to you.
Ah.
You have treatment versus control would be level 3, fixed effects, so they sink down to level 2. And so then it stays 2 levels.
Ah, yeah, okay, yes. In that case, let's say that we have 2 treatments with the hybrid approach. You don't need the 3rd level because that's not feasible. But let's assume that we have a 3rd level. In that case, the level 2 becomes within the 3rd level. The nested structure is the same. So the level 1 now will be nested in units at level 2 and level 3. The level 2 is nested in units at level 3, and the level 3 is the higher thing. So in that case, your level 1 fixed effects are level specific for units within units at level 2 and level 3. And your level 2 fixed effects are within fixed effects with respect to the level 3, and the level 3 can be contextual or between fixed effects. But that's something that we will cover next.
Not there yet.
Yes, but anything, when you add a layer, things will keep their structure. They will be nested, but you are changing the references because you have more levels. But things will stay consistent.
I have no question.
Yeah.
So if instead of assigning treatment and control at the hospital level, we assign, I don't know, so like each hospital is doing both, treatment and control group. Then we have 50 hospitals involved. Then the treatment would be a level 1 treatment, right?
In that case, I think we will have a 3-level structure now.
Yeah, there's an intermediate level, I think, that you just created, because there would be groups of people within a hospital getting control and groups of people getting treatment within a hospital.
Yes. And that's something that what we are doing with RONC in this longitudinal project, in which we have students within time, within states. Each state was measured 19 times over time. Every state has that structure, and within each specific time and state occasion, we have a set of unique students. So in your example, if we have a set of unique patients within treatments, within hospitals, we could have a 3-level structure. Although with 2 units at level 2, I don't know if we could do that.
But it's not just 2, it's 2 times the number of hospitals.
Ah, because yes.
It's not just 2.
Yeah.
So in that case, like, if you're able to assign your patients randomly to control versus treatment within the same hospital, then you're on a better leg to stand on in terms of controlling for individual differences and such. But then you have to make the argument that this group had no idea what was happening over here, and
Yeah.
there was no crossover or
Yes.
any of that stuff of any kind.
And that would violate one of the assumptions we have in design of experiments.
Yeah.
There was one assumption about the spillover effect.
Yeah, there's no free
Something
lunch,
like that.
basically. You're always going to have some limitation
Yes.
of what you're doing. It's just a question of what.
Yeah. Yeah, thank you.
Thanks for the discussion.
Question?
How do you decide what is the level 2 predictor? I guess my question is like, can you say patient nested between control and treatment group, and then the hospital will be level 2 predictor?
Yeah.
It can work either way.
No. The treatment would be a hospital attribute in this example. It depends on the sampling dimensions. In this case, the structure is patients in hospitals. So at level 1, you can have patient characteristics, and at level 2, you can have hospital characteristics. In this case, the treatment would be a hospital characteristic or a level 2 attribute. So it depends on the structure. That's something that you know when you look at your data. You know that you will have students in classrooms or patients in physicians, so and so on.
Yeah, I think the students in classrooms is probably a cleaner example because of the differences in where treatment versus control can be randomized. So, like, if I have, like, my kid's in the 5th grade, right? His teacher this year is Mrs. Hanrahan. So I could collect information about Mrs. Hanrahan relative to Miss Starr and Miss Keith, his previous year's teachers, about how long she's been teaching, whether she has a master's degree, whether she's certified in this, that, and the other, how big her class sizes are, etc. And my son and all his friends inside her class, those variables would be constants for them because they're all part of Miss Hanrahan's land, right? So in that case, teacher characteristics for classroom level variables, like class size, would be level 2 measured variables that could become predictors. And then my kid's test scores and his behavioral attributes and his personality and all his things, those would be student predictors potentially. However, to the extent that students are not randomly assigned to their teachers, they can also become teacher things. And that's where it gets real tricky. But generally speaking, if you have a characteristic of the cluster, and it would be constant for everybody in that cluster because it's a cluster thing, that's a level 2 predictor. Yeah. Oh, bonus question. Sorry, Vladimir, I'm jumping into your train here.
Yeah.
Can you think of a way that we would figure out if a variable is measured at level 2 or level 1 if you had no idea what data set was happening and someone just handed it to you? I bet you know, right? He knows where I'm going. Okay, I'm going to sit back down.
Should I say something?
No, let them talk.
Yeah.
I'm throwing it out there. If you had no idea, someone handed you a data set, right? That happens. How do you figure out if a given variable is level 1 or level 2?
Finding your variances and covariances, or at least they give you a hint. You know, if things are more related here in different pockets.
Maybe looking at the predictors.
That would be a predictor. That variable would be a predictor. The thing is, how can we know if that predictor or that variable is a student thing or a classroom thing, let's say? What will you do?
So I'm thinking two things, just from the understanding of the data sets. I'm looking at the data sets, at least to have some distinction. So if I see the level goes from, oh, this variable measures student thing, and this one measures the higher level thing. From that, I could deduce maybe this could be structure, and that would, or in another approach is to just create the empty model and using the global application. What's that? And then see if I have the right value, yeah, ICC.
There we go.
That would be 0, yeah.
Yeah, so ICC of 1, what's that tell us?
That's
Level 2
completely
variable.
level 2 thing.
ICC is 0? Not going to happen.
Yeah.
Stay tuned.
Yeah, I was thinking that in R at least, I would use the length of the unique values. So let's say that at level 2, we have 100 classrooms and we have 1,000 students. If that's a cluster thing or a classroom thing, the length of the unique values should match the number of unique units at level 2. That would be 100. But that's a lazy approach because some variables that doesn't have much variation. So they can be level 1 things, but we can have just a set of unique values. So that's the lazy approach.
Oh, I like that one too. Pragmatic.
Question 3 says, what's the common underlying feature of general linear models or generalized linear models that make them insufficient for multi-level data? And here I read all correct answers. All of you mentioned this idea of independence of observation, so great. And that will be a problem in nested data because we can have 3 different problems at least related to the violation of this assumption. We can have problems based on the correlated residuals. That's linked to the bias standard errors of our estimates. And especially, we could have smooth fixed effects in our models. And we wouldn't realize about that issue in our models. Was that clear? Why we shouldn't use multi-level single-level models with hierarchical data? Clear? Awesome. Question 4, how is ICC1 computed? And what are the 3 interpretations? So here I will go to Lisa's slides quickly. What's ICC1 first? What's ICC1? What would you say about that? Yes?
I'll try to interpret the proportion, or no. The proportion of the variance in level one variable that can be attributed to cluster differences.
Between cluster differences, yeah. And here you have the formula. So please remember that in this case, this tau square U0, that's the variance of the random intercept. The model won't give you the specific random intercepts for each cluster, but the variance. That's the model parameter. That's why in the empty means model, we say we have 3 parameters, because we have the fixed intercept, the residual variance at level 1, and the random intercept variance at level 2. Okay? So in this case, we know that at level 2, we have the random intercept variance, which represents this idea of how much of the outcome variance is attributable to between cluster differences, between cluster mean differences specifically. Yes, words. Words matter, yes. So, let me go back to this part. So, one of the interpretation is the proportion of total variance, total outcome variance, that's between clusters. We could also say that that represents the average correlation of persons from same cluster. So, that could be, the ICC1 could be also interpreted as an effect size of cluster dependency, okay? And this goes from 0 to 1, and as Lisa said, when we have, for instance, something like 1, we know that that would be a purely level 2 thing. Most of the time, what I've seen in practice, ICCs between 0.15 and 0.20, which is a lot, I've discovered in educational data. In other projects, I've seen 0.03, 0.05, which is almost nothing. But that's something, and we must make decisions about those things. Finally, question 5 says, how does ICC2 differ from ICC1, and what's an important caveat in thinking about ICC2 as a measure of reliability? You would also write about this one. What's the difference between ICC1 and ICC2?
Besides formula?
You could give the formula, but then what does the formula imply?
Yes. And what's the caveat there?
Caveat's not in the slides. That came out from classes.
Yes, I'm looking for this one. Yeah. So what's the difference?
I was going to say, well, the difference is ICC2 is the reliability of the cluster mean difference.
Yes, exactly.
I said, I don't know if it's right, but I said the caveat is that reliability can just, we talked about in class, reliability can be improved by just adding more.
That's one thing, yeah.
Be careful of.
Yes. And that comes from its interpretation from a measurements perspective. That here, given that we know that the level 1 sample size is doing something, when we increase the level 1 sample size, reliability will improve. What kind of observations or what kind of items doesn't matter, just more.
Yeah.
But that's,
People are the items in this case.
yes, people are the items here. But that's not the caveat. What do you think about it? Reliability, what would you say, given that's trying to capture the reliability of the cluster means? Any ideas?
No, I can read what I wrote, I'm not gonna say it's correct.
Yeah.
A high variability in the cluster's individuals could overpower the measurement error, leading to a higher reliability.
Not quite related, because in this case, I think, well, this is tricky because this is something that we will discuss in class briefly, but this is related to the idea of how much we have at level 2, how much random intercept variance we have at level 2, or how much cluster differences we have. So let's say that because this number, what it is this number, and what happens when this is low, for instance, let's say 0.2, 0.4, 0.6, what is saying that signal? Well,
There's a low amount of variability between the cluster means.
well, sometimes we can have a low
Well,
reliability.
Relative to the leftover variance. Because if tau is very small,
Yeah.
or a small percentage of this, that means that everything left goes to this other piece. That means that that's going to become large, and that's fixed. And
will be.
Therefore it's going to get small because this is small compared to the total.
They compensate to each other. But the caveat is that sometimes the reliability can be low just because we don't have a lot of variance at level 2. So this is related to how to interpret this value. And sometimes it can be low just because we don't have a lot of variance at level 2. So that's something that we can consider. Sometimes reliability won't be a large thing just because we don't have a lot of between cluster variation. So that's something that we wanted to discuss too. And that's all. Thank you so much for your attention. Questions? Are we good? How do you feel? In terms of thumbs? Great. Thumbs up. Great. Thank you, Lisa. Thank you.
Applause. I love this. Yeah, I would say that your answer is like the positive version of not a lot of differences means not a lot of reliability. Like, I don't know if I'd use the word overpowered, but yeah, if you have a lot of differences, you have a better shot at getting high reliability. But you're also right that if you have a giant cluster, then things are going to look better than otherwise. So it's just, it's different than a typical reliability statistic, I think. There's just a little extra layers. I can imagine that this is quite discipline specific as well. Yes.
Nobody asked, but what's a smooth specific?
Oh, we haven't talked about that yet. That's why they haven't asked. That's a vocabulary word that is forthcoming. All right, and I didn't, Vladimir, you didn't do the last question.
Oh, sorry.
Would you, so all of you participated, most of you are aware of this. I like to collect theme songs at the beginning of this semester. This can be if you were playing in an arena, like what would come on for you, or it could just be a hype song that is meaningful to you. Do you have one you wanted to share?
Oh, no.
No?
This semester I didn't do any.
You don't, so you want to think about it and get back to us then?
Yes, of course.
Okay, Erica, do you have one? No? Not off the top of your head? No. Does anyone want to share theirs?
I will say that I cheated. My wife answered my question. This is true.
Yeah, he wrote this. It's
I
fair.
even wrote this. I cheated. I said, okay, what would be good for me? My wife said, believe it or not, from Greatest American Hero theme song.
A few of you know, they're like, what?
What?
You're going to have to ask the Google.
Yeah.
Yeah, it's very 80s. It's the second I saw that, I was like, I started singing it in my head. It was like, believe it or not, I'm walking
Well, my wife
on
said
air.
she
That one.
watched it so many
Yeah.
times with her dad too. Just,
Yep. Yeah, I picked one too. And I posted the YouTube playlist I put together on Icon. So if you want to participate.
This time.
So this one, I always pick these intentionally, and I had to think about it a lot this time since it's the last one. I decided to go with Matthew Wilder's Break My Stride, another 80s song. Ain't nothing gonna break my stride, nobody gonna slow me down. Oh no, I got to keep on moving. So, there we go. Oh yes, now I get applause for my lackluster singing. No, don't cheer for that. Don't encourage me. But yeah, that's my choice for this semester here.
I don't hear you coming.
Oh yeah. I'm 47. Take me. I want to be a pop star. No, that is not going to go well. But fortunately, my true calling is making really, really detailed handouts of syntax and output. That's really what I was put on this earth to do. Am I right? Mm-hmm. So, should we rejoin the handout? Look at the numbers that go with the example that we started. So these are maybe fake data. They've been beat to death in many different tutorials and textbooks, and I went ahead and borrowed them for this purpose as well. So we've got 7,000 and some odd students at level 1, within 160 schools at level 2. Now note, these are maybe high school level things. So students within schools is the level of specificity at which this example is set. But what we're skipping over are all the different rooms that students in high schools are part of, right? Students have like 5 or 6 different teachers each semester, and then they change classes halfway through the term or each quarter. So there's a whole lot of clustering and nesting that in the middle that's just being smushed over. So just keep that in mind as a caveat. So we got through data stuff. We looked at descriptive statistics. So the descriptive statistics for level 2 variables in the full data set, for example, math is the outcome that we're going to be predicting. The full data set says it has a mean of 12.7 on a scale of whatever that means, which is why I think this data are fake, because a math score of negative 2.8 is not something you often see in test scores, but whatnot. So 12.7 in the full data set, but only 12.6 something in the level 2 data set. So just keep in mind that the means are not the straight means, they're the means of the means in these things. And that will be true of the slopes too. They'll wiggle around for same reasons once things are random. Let's see. We're going to have two predictors, whether the school is public or private, and then the size of the school. So I am rescaling this and centering it at the same time. So I want to make it so that my reference school has 1,000 children in it. And then I want to divide that by 100 so that my slope is per 100 kids as opposed to per kid. That keeps the numbers from getting too small. And I have actually seen models break from predictors that have too big of scales where the unit is too small. So just keep in mind that that can actually cause estimation problems. Did all the same things in R. Can I get a quick survey? How many of you are using R to do your homeworks in this class? Okay, how many Stata users? Got those ones? Okay, all right, so just keeping the relative balance, but I'm not gonna forget you, don't worry. And if you prefer to follow along in the source files, they have all the output from all the models so that you can have whatever pieces that are not being emphasized. But we went through model 0, meaning there is no multi-level structure. I did this mainly for pedagogical purposes. And we saw that it will return the overall unweighted mean and the overall variance of this variable as part of that. Then adding in the multi-level aspect. So Stata users, the new piece of the code that looks unfamiliar up to this point probably is this here. Bar means, hey, this is going to be a multi-level model, and you would have multiple sets of bars for multiple levels. It wants to know the ID variable that connects the rows from the same cluster together. Colon then is where you would list whatever terms you want to have random effects. The fact that there's nothing here means that it's just a random intercept only, which is the default. And we're going to use REML estimation, residual maximum likelihood. And I am saving the results of this to do math on later. So I think we started going over this much, maybe got through most of it. Does that sound about right? Should we do the R version? Oh no, we didn't do this part. Okay, I do need to go through that part. All right. So in Stata output for this empty model, by the way, synonyms for empty model, unconditional means model is another word that you will hear for that. So it is a common, dare I say, the most common starting point is to just estimate this baseline model to try to figure out how much variance you have at each level as a logical starting place. So at this point then, after we have a 2-level model, meaning I've taken all the variability in math and I've let the model split it into what is school stuff and what is student stuff at level 2 and level 1. Our new mean of math is the weighted mean that we saw earlier, and our variances have been split into what is due to school ID, so 8.6. What would I call that number? What's a verbal label for that? Yep. Intercepts. Need one more word in front of it. Starts with an R.
Random.
Random. There we go. Yep. This, I would call this level 2 random intercept variance. That means this is level what? Not a trick. 1. Yeah, or just what we used to call residual variance. So the terminology here shifts a little bit. In single level models, you talk about variance and residual variance. Like a variable has this much variance, and then we predicted it with stuff, and now it has this much variance left over, where the term residual means left over. In this class, I'm using the word residual to refer to level 1 variance specifically. Level 2 random intercept variance is what I'm using to refer to this. And I just want to highlight that to you because once we put in, say, a person level predictor, this will become the residual of the residual variance, right? The leftover part of the student level variance. And for that reason, some people call these level 2 residuals because they will become leftover. So I'm not going to do that, okay? I'm going to stick with the terminology. This is random intercept variance. After we add in level 2 school information, it will become level 2 random intercept variance left over or remaining. Likewise, this is level 1 residual variance across students. It will become level 1 residual variance left over after adding predictors. So terminology matters, words matter. It's real easy to get lost in these things. And not helping things is that different places use different words, even when they mean the same thing. So I'm going to give you all the words so you can hopefully talk to anybody. This thing right here, What's that telling me? We talked about this last time. LR test versus linear model.
Likelihood ratio test.
Yep, likelihood ratio.
And you're comparing it to the, well, the default is comparing your model to the empty model?
Close.
No.
Close. Who wants to help him out? It's a model comparison. It's a difference in -2 log likelihoods between two models. Right idea, but not quite. Empty with respect not to the predictors, but with respect to the random effects.
Oh.
So it takes whatever you have for predictors in your model, and it re-estimates that model, taking out whatever random effects you have. And then it compares the two. So it keeps the fixed effects the same. It compares the variance structure to see what is needed. So in this one case, because the only thing that's at level 2 as a random effect variance is the intercept, it's just comparing that one thing. So two different versions of an empty model. Essentially, it is doing what I did manually with model 0, where there was no random intercept, and it's doing it for us. The O1 thing, that's a recognition that this should be a mixture chi-square test. Critical value of 2.7 rather than 3.84, who cares? P-value is wildly significant on this level of chi-square. So this is the significance test that goes along with the intra-class correlation. So do we have significant dependency? Yes. How much? 18%. Those things go together. And I wouldn't necessarily need to report a significance test for the random intercept, but in certain disciplines, if you need to prove that you're in multi-level territory, you might have to report that as evidence. Okay. How are we doing? Okay, Stata folks, here's how you can make Stata do math for you. It's kind of a pain in the butt, and I wouldn't blame you if you just got out your calculators. But since I'm showing the R folks how to do the same thing, I want to be fair. So there are 3 parameters in this model. There's 1, there's 2, there's 3. When I ran the model, I asked it to save the results to a matrix. So this is an internal object in Stata that I'm calling model 1. Now down here, I'm asking it to print that saved result. So right now it is printing a saved result of the log likelihood of the model, and then I told it to multiply it by -2, giving you the -2 log likelihood that will show up on your output that goes into the homework system. Now I'm asking it to print the saved output from the model so that we can do math on them. So the first column, it goes in order of the output, by the way. So the first column is the fixed intercept of 12.6, its standard error, its t-value, its p-value, and so on. The next column is helpfully labeled LNS, I'm going to go with 1_1_1. Seriously. Yeah, we're all shaking our heads like, what? Why? I'm like, well, the second number was random intercept variant, so that's what it should be, except that's not an 8. Turns out behind the scenes, what Stata actually does for estimation is estimate the log of the standard deviation of each of these sources of variance instead, to keep it positive. Because logs can't, that keeps when you exponentiate, it keeps the variance that results positive. So this is the log of the standard deviation of the random intercept variance. Likewise, the last one is always level 1 residual variance, and this is the log of the standard deviation of the residual variance. So this code down here is meant to recreate what I was able to do in an R package that I'll show you in just a second, and I think I did it myself too. ICC2 is what I'm computing here using the saved results. So in comments, I have the formula. So intercept variance over that plus residual variance divided by the level 1 sample size. Note the line continuer here. It's 3 thingies, 3 slashes instead of 2 so that it keeps reading. And so then what I'm doing here is feeding it the pieces. So if I just focus on that, that is from model 1, the first row, the second column is pointing to that number. Then I'm squaring it and then exponentiating it and then squaring it. So we're unlogging it and then we're turning it back into a variance. And I had to find this on the internet. There's no way I would have figured this out on my own. I asked the Google, and that was how I got here. So then I have the random intercept variance term again. I have the residual variance term. And then at that point, I just gave up and stuck 45 in there as the average cluster size. But I'm sure you could access that in the saved results somewhere as well. So then if you ask it to display, it will print out the answer for you. So the ICC2 that was computed. So whenever you're trying to do effect sizes for like R-squares, random intercept confidence intervals, these kinds of things, you can access saved information in Stata. Now the good news is that if I were to do this analysis on a different data set, and I wanted to reuse this code, what would I need to change? Only one thing. I would need to change the 45. Yep, and if I did the extra legwork to figure out where I could access 45 from inside the saved output, then I wouldn't even have to do that. My hunch is that I could do it from, let's see, this number right here. Average observations per group. So it's close, but I wanted to round to keep it easier. So that's the advantage of actually going to the trouble when you're computing these sorts of intermediate results to using code to do it, is that then your code is reusable. Also, we have random intercept confidence intervals. We talked about this before, right? What does a random intercept confidence interval tell me? Let me hide it. Who's feeling brave? Are we talking about a 95% of repeated samples, the population, something?
Interval for likelihood of mean, of the cluster means being in this interval, I think, yes?
Yeah, we're trying to describe the expected variability that is implied by the random intercept variance. So we start with the center as the fixed intercept. That's the mean of the cluster means. And then the formula essentially does two standard deviations around that fixed intercept. So the square root of the random intercept variance is the random intercept standard deviation times 1.96 for a 95% interval gives us this. So then this is the range of school mean math outcomes across the schools. That to me, if I were an administrator who's not familiar with statistics, this would be more informative than 18% of the variance. Right? Oh, somewhere between 7 and 18 on average, that's a lot of variability. Okay. Questions so far? Our folks, I don't want to leave you out. So we're using Elmer. That's what we're going to use this whole semester. For those of you who went through the longitudinal class, we did not always use Elmer because for some models that have a correlation among the time-specific residuals, Elmer does not do that. In this class, people have to be exchangeable. There's really no other choice. So there's never a residual correlation that would need to be introduced. So Elmer is just fine. REML is true. Can you guess what it would be if I wanted to use ML instead? False. And sometimes these things are in quotes and sometimes they're not. You just have to learn. Formula. So math is my outcome. Squiggle 1 is where I'm referring explicitly to the fixed intercept. Squiggle is like the equal sign for the equation, that it can't be an equal sign because equals are already used for arguments. So they got to invent new things. Now I do this for my own sake because in pieces of code where I have to count out the number of fixed effects, I'm inclined to skip the intercept unless I leave a place for it in my code explicitly. Yeah?
I've seen in places where they put -1 to try to get rid of an intercept.
Nope, it's a 0.
That's what I thought, but I was because that's what mentioned in the article someplace I read, like that's confusing.
In a different package, that could be true.
Oh, in a different package maybe.
That's, this is why R drives me insane, is because there's no standardization. So in this package, and in a few others that I've seen, you can shut off the intercepts by putting a 0 there explicitly. Otherwise, it's implicitly a 1. But this is the new part, in parentheses. So that is our random intercept for school ID. And the 1 is meant to mimic the idea that you have a column of 1s as the pretend variable that would be multiplying this if you wrote it out as a matrix equation. So that's referring to that. Yeah, and school ID is the case and space sensitive ID variable that connects the rows that belong to the same cluster. By default, it does not spit out -2 log likelihood with enough degrees of freedom, so I ask for it to do that. And I'm also asking for a model summary using what's known as Satterthwaite degrees of freedom. That has been shown to work well for multi-level models, and it generalizes across packages and programs, so that's what I tend to use. Yeah, that's the close agreement. So over here then, deviance, for our folks, that's what goes into the homework system. That's your -2 log likelihood value. That acts as a thumbprint to let you know that you have the right model, the right contents of your model in terms of outcomes and predictors.
Not necessarily central.
Right. So secondary to that, the next question is almost always, what is the fixed intercept? Because if you have the fixed intercept wrong, that means your definition of what 0 means for at least one of your predictors is wrong. So your model's right because it has the right contents, but the scaling of it is not what was intended by the instructions. And so that would be the fixed intercept would catch that aspect. So it tells you, helpfully, how many level 1 units and how many level 2 units. Make sure you stop by this section of the output, verify that that looks reasonable. Make sure that your data are being read in the way that you had intended. Stuff happens, you know. By the way, out here, this is me being nice. You will not see labels on your R output telling you what the stuff is. It's not going to happen. I started doing this back when I was a postdoc building these handouts using SAS, and my students called it Proc Lisa. So I like that one. Actually, if I were going to make an R package, it would call LISAR, is what I would do with a capital R at the end of it, because that's what it says on all my airline tickets, because my middle name is Renee. And so it says LISAR on my reservations. So I got a head start in building my package. Not going to happen. Likewise, for the fixed effects, I have this labeled as gamma 0, but that's just me being nice. You would think that of all the options that are built into Elmer and Elmer Test as an add-on that gets you extra things, that ICC would have been one of them. You would have been wrong. So I found another package that does that. So there's a package called Performance, of all things, that ICC is a function, so I'm using that. It works with Glimmer as well as Elmer, so generalized versions. Renova, that is how we're going to do likelihood ratio tests. In R, this is called different things. Sometimes it's called Renova, sometimes it's called ANOVA. It just depends on which package you're working with. So Renova is like the R is for random effects. So the interclass correlation from this function is printed down here. Adjusted versus unadjusted refers to what it would be with predictors or without predictors. At this point, they're the same number because we have no predictors. Then down here, ANOVA-like table for random effects single-term deletions. Okay, it has nothing to do with ANOVA. Don't let that into your head. It has nothing to do with it, absolutely nothing. But what it does have is the number of parameters and log likelihood for the current model, and then one in which it took out this random intercept. So it's essentially fitting the nested model without the random intercept for you, and then doing the likelihood ratio test for the comparison, ignoring the fact that it should be a mixture chi-square. But if we have 0 to 16 decimal places, we're pretty good on that score. So I have the same caveats in terms of what the mixture chi-square thing would have been anyway. And then last but not least, found some packages to do ICC2. And they had options for weighted versus unweighted, which I'm not exactly sure what they do, but you're welcome to try and figure that out. Here's what the numbers are under each one. You can see they're pretty similar. So the 908 was what Stata gave me. And if you're like, that package won't work for me, can I just do it with the saved output? Yes. So the same technique that I just showed in Stata in terms of saving the results, accessing those saved results, and making it do math. There's a bunch of different ways to do that. Bladimir and Erica are way better at it than me, so if this breaks, go to them. But what I do here is, so model 1 is the model object that has all this stuff in it. I asked it to print as a data frame a function called varcore from model 1 that accesses the variance components as they were estimated. So it's organized then by what the variances refer to, vcove is the variance, and then SD core is the standard deviation. For models that have random effect covariances, this becomes a correlation instead. So now that I have this table, I know how to access the numbers in the table. So ICC2, the numerator of it is your random intercept variance. So within this table, as data frame, VARCHOR function to access the numbers, I want row 1, column 4, because it's counting 1, 2, 3, 4. So that is putting the 8.6 in there for me. And then likewise, 2, 4 is that 39 for the level 1 residual variance, and then there's the 45 that I just stuck in manually that I'm sure you could figure out a way to fix too. Last but not least, doing the same idea for a random intercept confidence interval. So fixf is a function that returns the fixed effects. I put this in here just for clarity. I want the first one. Right now there's only one, so it would have worked either way, but there may be more than one. And then the next part goes in and finds the variance for the random intercept, turns it into a standard deviation, and then does the 1.96. So those are the same limits that we calculated in Stata. And last but not least, a design effect. So in this sample, we have an intraclass correlation that's relatively high, 0.18. We have an average of 45 people per cluster, -1. So that creates a design effect of over 7. So that means if I were recruiting people for a study, I would need 7 times as many people as if I had a simple random sample where the kids weren't clustered in school. Bad. That's a lot, isn't it? Yeah. Okay. How are we doing? Thumbs-ish? Any that you want to hear again or hear differently? You have a question, Dan? No? Fair enough. Yeah, it takes a while to sink in. I can't even tell you how many times I've read the Snyder's and Bosker book. Like, it's probably a dozen. Like, and every time I pick it up again, I get something new out of it that I didn't notice before. So yeah, this is just going to land in layers, right? Just get used to that feeling of being just a little overwhelmed at all times. It gets better, right? You're like, a little bit? Yeah. It gets better.
Good practice.
Well, it's going to get better, and people will eventually pay you if you learn this stuff. How's that? There's some really concrete motivation in actual money, authorship, or both. All right, 139. I'm not thinking we have the energy to spend the next 5 minutes on a brand new topic. Do you? I don't think so. Yeah, no. So Thursday, I have Zoom. Yes, I was just going to remind folks and pull up the course website real quick. So yes, Thursday is Zoom only. I put up lecture 3. I'm almost done with example 3, but realistically, we're not getting to it. So just plan on, let's finish lecture 2, example 2, and maybe we'll start lecture 3 if we're feeling feisty. How's that? But on Zoom. On Zoom. Okay.
This closed.
This room is being used. Yes. So, all right. I will see everybody then. Go out and enjoy the weather. Hooray. Yeah. Happy Garbage Day, by the way, too. Can't forget that.